Okay, this is a different kind of video and we'll see how this goes. Um, I find all these AI and large language models and coding agents and all this stuff endlessly fascinating. So I often get into these like kind of discussions, learning sessions with Claude or ChatGPT or whatever, mostly with Claude though. Um, and oftentimes such interesting things come out of it, and I don't always know how to compress it into a video. And also, I don't want to pretend like I know all these things off the top of my head. So I figured maybe I just work through one of these sessions in a video format and we see how that goes. So something I've been thinking about is counting tokens, because I still hear and see quite a lot of people and companies fixating on counting tokens. And I'm not saying you shouldn't, because of course there is money locked into those tokens. They're not free, they cost money. And businesses don't have endless money. Some seem to, but most businesses don't. The thing is, tokens are complicated and counting them is kind of hard, predicting what it would be. So I have a different proposition that I'll posit at the end. But to begin with, let's dig in a little bit to what is a token and what makes up one token. And believe me, it's kind of all over the place, but it is very interesting. And of course, how many tokens is sent between you and the provider and back, and it's not entirely in your control. It's also definitely not only the things that you've typed in and that it has generated. There is many things that play into this, and we'll touch on a lot of them as we work through this session I had. Um, but of course, a lot of things, is like the system prompt, the changes in the tokenizer, and I asked some questions about that we'll also get into. There's the message role wrappers, and I'll show you now what I mean by that. There's your agent skills, the language, and here I'm not necessarily talking about the programming language, but the language like Afrikaans, German, English, Italian, whatever. All of these things have an impact. And the tokenizer itself, of course, changing and all of these kinds of things. So let's start off by just looking at a couple of things here. And we'll take this piece of text here, just hello with an exclamation mark. And if we jump into OpenAI's tokenizer over here and we run this, we'll see it's two tokens. And that is because hello is a token and the exclamation mark's a token. And this hasn't changed since GPT-3. Like the tokenizer has changed, but it still tokenizes this the same way. And you can see here at the bottom, let me actually zoom in, how these are separated. So that's one token, that's another token. And so already here we can see, maybe you would have thought this is a single token, but no, it's not. And then there's some other things that's interesting. For example, here, you might also have thought, well, three tokens, but okay, we now know about this, so four tokens. And it's exactly correct, but we'll also see how this space works. Like this leading space is made part of the word is as a single token. And here again, the leading space is part of accessibility, making up that single token. And then if we switch over here, we can actually see that under the hood, each of these are assigned a ID, a token ID. And there's some really interesting things there that we'll, when we look at emojis later. And but here's the other interesting thing. If you take accessibility and you remove it out of that sentence context and you use it by itself, it's two tokens. Now all of a sudden it's so context matters. It splits it up into two tokens with two separate token IDs. So see already what I'm talking about? And then the other one that often happens, that changes between models and tokenizers, more specifically tokenizers, is how numbers are tokenized. So you could look at this and be like, I have no idea how many tokens this is, maybe 10, but depending on the tokenizer, it's going to be different. If we look at this one here, it's actually 4 tokens. And here we can see what's happened is it's grouping them in groups of 3. And each of those is collapsed into a single ID. And we'll later on see what those IDs are. And if we switch back, so even the tokenizer with GPT-3 But look at it subtle. It's a subtle difference though, that I kind of just noticed. So if we look between GPT-5 and GPT-4 3.5, same, but if we go to GPT-3, even though we end up with 4 tokens, we have a group of 3, a group of 2, a group of 3, a group of 2. So that's interesting. And if you look at the IDs also change, and we'll see why that also happens, because it's a different tokenizer. Okay, so, and then it gets even crazier when we get to emojis, but I'm going to leave that separately. But the other thing that's interesting is if you look at code, like this simple piece of HTML, you can see how interesting it is decided to group these. So we have 7 tokens here, and we can see this A is grouped, but here we have just the A letter as a single token all by itself later on here. And then we have the leading space plus the href, a single token. And then interestingly, we have the equal sign and everything, including the closing or the greater than sign, a single token. Then we have the contents, and then again we have our opening or our greater than sign and our forward slash being a single token. And then let's see if we go all the way back and look at here. Now we have 9 tokens. So we've gone down to 7 tokens between GPT-3 and GPT-5. And you can see the difference. For example, here it's taking these 3, but then it's keeping these 2 as a separate one. And also here in the beginning, you can see the A is a single, A is a single. But over here, it's actually been merged into one token. So that is super interesting. Again, we'll get to emojis. And what do I mean by message role wrappers? So if we look at tick tokenizer, sorry for the white flash there, don't think they have a dark mode. We can see here that we have 2 prompts. We have the system prompt and we have then the user. And here we can see, this is what I mean by that. So this marks the start. Here's the separator. And then here's the message. And there's the end. And then we start a new one, which is the user, separator, end. Start a new one, which is for the assistant, separator. And you can see each of these also uses a token. But of course, I am start here, I am start there is the same token ID, right? But again, you can see I have not typed in anything and we're already using 16 tokens. Okay, so that's what I'm saying. There's so many things that plays into this. That's not just, and then how tokens are broken up by the tokenizer and then how it's also stored. This has another impact. So now let's jump into this thread. So this is where the thread started. So I'm going to skip over quite a bit of stuff here, but so nearly everyone uses byte level BPE, and that is byte pair encoding or a close relative. So common English words sum out or come out as a single token. A leading space usually merges into the following word, and we just saw that. And rare words, non-Latin scripts, and unusual identifier fragments. So here it says if your model is roughly 1 token per short word, more for anything unusual, that kind of survives across providers. But what doesn't it's not the things you want for budgeting. So vocabulary size and training corpus differ, and this has an impact because then the merge tables are completely different. And there's also pre-tokenization regexes that differ, which determines where a token is even allowed to begin. And then there's other stuff about sentence piece unigrams rather than BPE. And then the thing we saw about digit handling, that is notoriously divergent. Some tokenizers split numbers 1 digit at a time, others in groups of 3. And so this alone can double the count on numeric data. And then also white space runs also matter a great deal. Something I want to try here just really quick is 1, 2, 3, 4. So I added 4 spaces, but we only added 2 tokens, right? 1, 2, 3, 4, 1, 2, 3, 4. We have added no more tokens. And this is because it might be that this is optimized for, or it's slanted towards coding in a way. And so this is very commonly seen in coding. Tabs or spaces, 4 spaces, 8 spaces, that kind of thing. So I can't unfortunately put it just a tab here, but you can see, so 1 space adds a token, 2 adds a token, and now all of a sudden, no more tokens are added. It's all being taken up, I believe, by token ID 309. Let's see here, if I delete here, now token ID 309 is gone, but hold up. So there's, now only this first one changes. Notice that? Interesting. Very, very interesting. Okay, let's head back here. So within single providers, there's nuance too. Some of you might have seen that when, I believe, when Sonnet 5, or maybe it was when Opus 4.8 came out, I think 4.7 actually, Anthropic introduced a new tokenizer that increased token count by about 30%. So that is another thing how things differ. Okay, and then I just asked about some ways, and it's like, okay, the only one that's actually published a tool like this is OpenAI. There is an API endpoint for Anthropic and Gemini, and Hugging Face has a tokenizer library that you can also use. Okay, links, further reading, da, da, da. But here is something that's interesting, of course. I am doing great, comma, thanks, period. So again, now we know that this is not going to be as many tokens as you might think, because again, I am with its leading space, doing with its leading space, great with its leading space, but then the comma and the period at the end, each being their own token. So here's also something that's very interesting. Between GPT-4 and GPT-4o, Aria, so we can actually go and do that. Aria is a single token, 2 tokens, because it's splitting it up between AR and IA, right? Whereas when you come back here, it's now a single token. Okay, so, and there's the accessibility one, and then the whole language. This is an Afrikaans, and we can see the difference between just that Afrikaans word, the difference between GPT-4 and GPT-4o plus. So these are, I believe, the different tokenizer or the bases. Not entirely sure. Maybe we can ask later. I'll include these links also in the description. So if you want to go play around with these, then you can find them there. Also, I'll link these further readings in there as well. Da, 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 da. So now we get into emojis. And I first kind of confused Unicode with code points. And it's an important distinction. But now things are going to get really interesting. So let's see where to go. So here's just some token counts, but let's move on a little bit from there. We can see there's quite a bit. Look at the big difference here. 3 tokens for the thumbs up versus 1. This one went from 3 to 2. And it's interesting how this happens. So even though our little heart token here is 2 code points and 6 UTF-8 bytes, then this one, it costs fewer tokens. So there's another thing. More code points, more UTF bytes doesn't always mean more tokens. So, but why not? Because what actually determines it is what's here. So BPE byte level tokenizers do not operate on the code points. They operate on the raw UTF-8 bytes, but that's also only part of it, and we'll get to the other details. In every byte value has a fallback entry in the vocabulary so that any input is guaranteed to encode. Whether a given byte sequence collapses into 1 token depends entirely on whether the BPE training process saw that sequence often enough to spend a vocabulary slot merging it. It is a frequency question about the training corpus, not a structural question about Unicode, but there's nuance to that, and we'll get to that. So, for example, if we take the little i's, well, let me finish this, versus thumbs up, structurally identical, 1 code point each and 4 UTF-8 bytes. But if we take this one, it's 2 tokens. And here we can see, like, this rendering is your input contained 1 or more Unicode characters that map to multiple tokens. So you can see that there, but then if we go back and we grab the thumbs up and we go back into our tokenizer, single token. So what gives. So nothing about Unicode express that. Corpus frequency does. Thumbs up is one of the most common emoji on the internet. So it earned a merge and the little eyes did not. And then here's another one that's really wild. And so I'll just copy it over here. And it's this little family emoji. And you might see it over here much better. 2, 3, 4 tokens, maybe? Well, 11 tokens, 14 tokens. So that single emoji is more tokens than a sentence. So a single glyph that costs more than a short sentence. And there's also, here's the language thing, like for example, this E with the, what do you call it? It says this here, blah, 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 blah. What do you call this little thingy on top again? Oh man, I forget now. Acute, the acute on top. Depending on how it's written, it can be 1 token or 2 tokens. Fun. Okay, so let's move on. So I just asked what BPE is, and it's a byte pair token or byte pair encoding. And the name explains the algorithm. It repeatedly finds the most frequent adjacent pair of bytes or of previously merged units, and this will become important later, in the training corpus and merges that pair into a single new unit, recording the merge in an ordered table, and repeat until the vocabulary reaches its target size. Okay, so let's move on. So I said, but then if two emoji have the same number of bytes, why is one collapsed into a single token and the other not? So as I said, I know that has to do with frequency with which it is seen in the training corpus, but is that it? And so frequency is the main driver, but frequency is doing more work in that sense, classic AI sentence. And there's 3 refinements. And so now we are really getting to interesting things. So a 4-byte emoji does not become 1 token by clearing 1 frequency threshold. It has to survive 3 successive merges, and the merge table is ordered, so each one must win its own round against every other candidate pair in the corpus at that moment. Crucially, the counts are measured on the partially merged corpus, not on raw byte counts. Earlier merges consume occurrences and change what the later rounds see. So the process is order dependent in a way that raw corpus statistics do not capture. Okay, so here's what's actually happening. Now here's something interesting. You can see all of these are in the same range, U plus 1F44, all of them. You can also see that they share this 3-byte prefix, all of them, F09F91, all of them. What's different is the last 2, is this last byte here at the end. And now we can see that this one is the 2 token, so there, 28823, and then 222. But look at this. This one and this one is the same because it's that token ID represents this 3 code or 3-byte prefix. So token 28823 is that shared prefix, and 222 and 233 are raw single byte fallback tokens for OX80 and OX8B. So this one and this one. And so, and these have their own single token unique ID, but it wasn't always like that. They actually, all 4 of them shared this same construct of 28823, comma, and then its unique single byte fallback. So we'll get to that in a second. So the first merges were never in doubt that F09F91 prefix accumulates counts from every emoji in the U plus 1F44X range collectively. So, which makes it cheap to earn. The expensive decisive step is the last merge, funded only by that emoji's own frequency. So these two won out over these two. And so that is why structurally identical inputs diverge. So that's the one thing. 2 other factors are generally in play. Pre-tokenization runs before BPE and splits text into chunks with a regex. Merges can never cross a chunk boundary, so the regex determines which pairs are even visible as candidates. and the vocabulary budget is fixed. So this is ranked competition. Emoji mergers compete against English words, code identifiers, white space runs, and every other language in the corpus, doubling the budget from roughly 100,000 to 200,000 is precisely why so many of these emoji collapse from 3 tokens to 1 between this and that, because literally just that budget doubled. So let's move on. So here I said, so 3-byte prefix is seen frequently enough to warrant merging those into a single token with ID that. But then on top of that, the full 4-byte pattern of this, which is the thumbs up, I believe, and the little hand that does that, all good, or I don't know, that little sign, seen even more often to warrant those being even further merged into their own single token with ID blah and blah. So the structure is correct, but there's something here that I got backwards. So, and this is kind of what I mentioned earlier now, which I only now know to be correct because I went here. The 4-byte sequence cannot have been seen more. Of course, when I read this, I was like, duh, because the 4-byte sequence cannot have been seen more often than its own 3-byte prefix, right? You can't see this more than you see this. You will always see this, and then the last bit is just added. So because this is also an occurrence of that, of course. So the prefix count is necessarily greater than or equal to the count of any single emoji built on it. And in practice much greater, since it sums across the whole block. So there's even more occurrences of it. The prefix is more frequent thing by construction. What the latter merge has to clear is not its own prefix. It has to be frequent enough to win its round against every other candidate pair skill competing for a slot at that point. And so the pair is this plus this. So that's what makes up the pair. And so now you can imagine if we kind of go back here, so we have this as a pair, this is a pair, and then as I mentioned, these two were also pairs of these three, and then in this case 8D, and in this case 8C. And so if we continue down that, it then says, so not its own prefix, but the pair still competing for a slot. And so by the time the tokenizer is deep into 200,000 slot budget, the competition has thinned out considerably, and a sequence with modest absolute frequency can win simply because the remaining field is weak. So the question is never, is this more common than its parts? It is this the best remaining merge available right now? And then one further precision, PPE only ever merges pairs. So yes, so that's why when I said the 4 goes into a single one, it's not the 4, it's the pair of F09, F91, and 8T. It's those two that gets merged. So the pair. Pair consisting of existing 3-byte, okay, exactly what I just said. Every entry in the vocabulary above the byte falls back into the union of exactly 2 earlier entries. Your auditing claim, though, is directly verifiable, and this is a nice detail for the video, which I'll make now. In TikToken, the token ID is the merge rank. Lower ID means the merge was learned earlier. So we can see that before this one was merged into a single token, the thumbs up happened, right? So we had the shared prefix, and then this was merged, and then in a later run, this was merged. So, and the IDs confirm the sequence, prefix first, then thumbs up, then that one. The same signal shows up in plain English where you can need to check it. So space quantum, space Zimbabwe, space isotope, and then all of these. So you can see the IDs are increasing. So it means the merged happened later. So token ID as a rough frequency proxy is fun on camera reveal, but it means the vocabulary is readable as ranked list of what the training corpus was made of. Okay, so I said, so all 4 used to share the 3-byte prefix, but at some point the pair of this prefix and AD cleared the bar, and this pair was merged into the single token. So yay, finally I got it right. And it extends further than the 4 I have seen. Like I said, all 16 emoji in this block share the same prefix. So they all sat in the same queue competing for slots as training progressed. So they all were these. So at some point, the first three became a single token, and then you had all these pairs sitting there with this prefix and then the single byte. And they were all basically over time competing for a single slot. And over time, thumbs up graduated. And then the question here is, so when thumbs up graduated, did that hurt the others by consuming prefix occurrences? And so it reduced the standalone count of the prefix token, yes, but it did not touch the count of the pair because those are disjoint occurrences in the corpus. This graduating did not make the eyes any less likely to. The order dependence earlier is real, but it bites when merges generally overlap. So the last piece is the one, let me see, this piece is not the one this counting happens in code. Oh, the last piece is that none of this counting happens at encode time. Training produces a ranked table, and encoding just replays it greedily. Take the byte sequence, repeatedly apply the lowest rank merge that is available, stop when none applies. For the eyes emoji, that means merging up to 28883 and then halting because no entries exist for this one. Encoding is fully deterministic and involves no frequency information at all. The statistics are baked into the rank ordering. So could other two token emoji graduate, so to speak, to a single token later during future training runs? And yes, we saw that that already happened. So this one cost 3 tokens and then it went down to 1. And so this is precisely the graduation. So the mechanics is not what later might suggest though. A trained tokenizer is frozen. The rank table is fixed and nothing ever appended to it. What actually happens is that a new tokenizer is trained from scratch on a new corpus with a new budget. And that fresh run, the pair this wins a slot it did not previously reach. So it is not promotion within a table. It is a different table in which the outcome differs. So because retraining reshuffles everything. So that's why we see those token IDs also changed. Token IDs are not stable across encodings. The same integer means different things in CL 100,000 base and O 200,000 base. Since a model's embedding matrix has one row per vocabulary entry, changing the tokenizer invalidates the embeddings entirely. You cannot swap a tokenizer into an existing model. You get a new tokenizer only when you get a new model. That is why tokenizer changes arrive bundled with model generation rather than updates. So 4.8, 4.7 was that big jump, and with that came a new tokenizer. So let me see, the movement is not guaranteed to be one directional. Vocabulary is fixed budget allocated by competition. So if a future corpus skews harder towards code, so this, I dug into this a little bit more. So if a future corpus skews harder towards code or towards non-English languages, those mergers can crowd out emoji that previously earned slots. Something that costs 1 token today could cost 2 in a later generation. Budgets do not simply grow to accommodate everyone either, because embedding table size and the output softmax both scale with vocabulary. A practical takeaway, token count is a property of a specific model generation, not the property of the text. Anything you can cache, budget against, or hard code has an expiry date attached to the model it was measured on. And that is kind of why I'm want to put more time into that skills order research, because again, there you need to understand whether your skills are still valuable or just taking up token costs against newer models. There's another or other thing I want to do with that, but that's a separate video. So identical input, roughly 30% more tokens. That is the Claude figure. So the opposite is also possible, which it already answered, which is basically something that's a token today could become 3 tokens tomorrow, depending on how the corpus is skewed. So it doesn't become rarer in absolute terms. The budget is fixed and the allocation is zero sum. So emoji can lose a slot purely because the competition it got stronger. So the competition for that slot got stronger, and now something else can potentially win out thumbs up. So emoji frequency could hold perfectly steady and thumbs up could still drop back to 2 tokens. The observed trend has run the other way. Vocabularies went roughly from 50,000 to 100,000 to 200,000 across OpenAI's generations. Each expansion collapsed more emoji into single tokens rather than fewer. So regression is mechanically possible, but there's no documented case of it actually happening for emoji. So the other caveat is that this is not purely emergent. Tokenizer training corpora are curated, not simply inherited from the model's training data, and providers weight them deliberately. Multilingual coverage and code density are choices someone makes. The pressure towards code is not only something that happens to the corpus, it is partly a decision about what the vocabulary should be good at. And that decision reflects what the model is expected to be used for, which is a very satisfying place to land. So, uh, what is the benefit of merging? In other words, why would a corpus skew towards coding, not merge an emoji, but instead merge something like href equals? So merging buys exactly one thing: fewer tokens for the same text. Yeah, everything else follows from that. Sequence length is the currency the whole system runs on. It sets the API bill, how much fits in the context window, and it says compute, and it sets compute cost. Because attention is quadratic in sequence length, halving the token count does considerably better than halving the work. A tokenizer that represents the same corpus in fewer tokens is strictly better along all three axes at no cost to the model architecture. So selection criterion is not, is this a meaningful unit? PPE's objective is literally compression. A merge whose pair occurs n times in the corpus removes n tokens from the corpus. And the greedy rule of picking the most frequent pair is just picking the merge that removes the most. So the reason merge tokens so often look semantically sensible, space const, space function, space href, is that frequency and meaning happen to correlate. It's a byproduct, not the goal. So a vocabulary slot costs the same regardless of what you spend it on, but the return varies enormously. In a code-heavy corpus, this might appear hundreds of millions of times. So that slot removes hundreds of millions of tokens, whereas that might appear, so the eyes might appear a few thousand times, same price, wildly different yield. The emoji is not rejected for being an emoji, it is simply loses on return per slot. So makes perfect sense. The cost side is what makes slots generally scarce. Every vocabulary entry needs a row in the embedding table and a row in the output projection, both sized by the model's hidden dimension. At a 200,000 entry vocabulary, that is a substantial parameter count on each side, plus a wider softmax. And so there's a second subtler cost worth mentioning. A token that earns a slot during tokenizer training, but then barely appears during model training, ends up with an embedding that was almost never updated. These are the so-called glitch tokens, and they produce generally strange model behavior when you hit them. Interesting. Karpathy covers this in his quirk section of his lecture, which I will link, and his memorable segment. Merging too aggressively has failure modes, not just cost. One last thing, which given you earlier a question about regression, looking for code typical fragments and found real example. So space class name, one token, class and name is now two tokens. Very interesting. A token that existed in one generation and does not in the next. That is the reshuffle observed. So this went from a single token to two tokens. So my question was, a company that builds the tokenizer, knowing that they are targeting a developer market, would then optimize the tokenizer to merge more byte patterns related to code than to general language byte patterns and emoji. In effect, lowering the cost of code generation, but as a side effect, potentially increasing the cost of generating documentation, as an example, because I was thinking documentation is prose, not code, but there's a big overlap here, and so it's not as simple as that. So again, direction is right. And the first half is true, but the second half needs adjusting. And it says because English prose is not who pays. So start with the lever, since it's not what optimize the tokenizer to merge more code patterns implies. So nobody sits down and picks that for a slot, the mergers are produced mechanically by frequency. What a provider actually controls is the corpus mix, the vocabulary budget, and the pre-tokenization regex, and a handful of explicit rules such as digit grouping, which we looked at earlier. And the regex is the most deliberate of those and the most clearly code motivated. GPT-4's encoding changed how white space runs are grouped specifically so that indented codes stop burning token per space. And that's the one we saw earlier, where all of a sudden I hit one space, two space, when I hit three spaces, all of a sudden the number of tokens stop increasing. So that was the design decision aimed squarely at code, and you can see the result. 4 spaces is 1 token, 8 spaces is 1 token. So, but that's correct. Skewing a corpus towards code does not meaningfully raise the cost of English documentation. So that's the part to correct. For 2 reasons. First, English mergers are cheap to acquire because English is enormously frequent. So the valuable one earns in the early rounds regardless of the mix. Second, and more to the point, code corpora are full of English. Yes, comments, docstrings, readme files, identifier names, error strings, commit message pairs, all of these skew towards English. And the competition is real, but it happens in the tail. What loses slot is everything with modest frequency and no compensating presence in code. So emoji, rare words, and above all, languages other than English. So we can see here the difference between English, Afrikaans, German, and isiZulu. Very interesting to me that 43 characters of isiZulu is 14 tokens and 53 of German is 12 tokens. It's a very small difference, but um, even Afrikaans does surprisingly well here. Well, actually, no, it doesn't. Sorry, ignore that. It uses more tokens for 13 fewer words than German. So identical character count between the English and Afrikaans lines, and Afrikaans costs 60% more. isiZulu costs 75% more. Since APIs bill per token and context windows are measured in tokens, that is a direct surcharge on writing in those languages. Smaller effective context, higher cost for the same content. And so here says this is a documented and much discussed equity problem, and it is the genuine downside of budget competition. So one footnote, in practice, the budget has grown rather than been reallocated, 50,000 to 100 to 200,000 across generations. So the trade-off has mostly been resolved buying more slots rather than by taking them from anyone. So my question then, so what sets the upper bound? Is there an upper bound? What I'm referring to here is the 50, 100, 200,000. As you stated, it went from 50. So there is no hard ceiling. The vocabulary could in principle keep growing since you could always merge longer and longer sequences. The bound is economic and it comes from 4 pressures pulling against each other. And this is very interesting, I think. So parameters, every vocabulary entry needs a row in the embeddings table. You heard that before, and a row in the output projection, each sized by the model's hidden dimension. At a 200,000 entry vocabulary and a hidden dimension of around 4,096, that is 0.8 billion parameters per matrix. Those parameters are spent on lookup rather than on reasoning, which is why the trade-off bites hardest on small models. A 1 billion parameter model with a 200,000 vocabulary would spend most of itself on the dictionary. Did not know that. Output cost. The model computes a probability over every vocabulary entry for every token it generates. Widening the vocabulary widens the computation. And during training, the logits, yes, tensor scales with vocabulary size, which is genuine memory pressure rather than a rounding error. So diminishing returns, which is the pressure you can see, word frequency follow a zip-d distribution. I'm curious what that is exactly. A small number of items are enormously common, and there is a very long tail of rare ones. So each doubling of the vocabulary buys progressively less compression. So this is interesting here. So English prose, CSS, HTML, JSON, React.js. Curious, like there it went into a negative. I haven't actually read this, by the way. This part I haven't read. English prose was already saturated at 50,000 slots. 3 encodings, identical token count, code gained substantially. So In other words, going from 50,000 to 100,000, there was no benefit, if I read this correctly. 100 to 200, no benefit. So you essentially have diminishing returns here. Increasing the vocabulary doesn't buy you anything. Like at 50,000, this was already saturated, as it says. Um, the React sample got worse, which is the class name regression. Aha! This all comes full circle now, because now the class and name is split into two tokens. So actually, when you went from 100,000 to 200,000, your compression here got worse, and your token usage, or yeah, token usage went up. So the second doubling was not spent on English or on web code. It went to multilingual coverage and the long tail. That is your zero sum reallocation method. And then rare token under training. Beyond some point, you are minting slots for sequences so rare that their embeddings barely receive gradient updates during model training. That is where glitch tokens come from, and it means an oversized vocabulary can actively hurt. Because those four pressures resolve differently at different scales, the optimum is not a constant. Tao and colleagues trained models from 33 million to 3 billion parameters across vocabulary configurations and found that the compute optimal vocabulary size depends on the compute budget and with large models requiring larger vocabularies, and that most large language models use insufficient vocabulary sizes. Interesting. Their estimate for Llama 2 70B was at least 216,000 rather than its actual 32,000. And raising a 3 billion model from 32 to 43 improved ARC challenge from 29 to 32. Interesting. Critically, the loss curve is U-shaped. For a fixed compute budget, loss falls as vocabulary grows and then rises again. So an optimum generally exists rather than bigger simply being better. And here's a, what do you call it? A paper for citation, which I will also link. So the honest answer is that 200,000 is not a limit anyone hit. It's roughly where the curve flattens for current model scales. And the research suggests frontier models could justify going further. So that is really interesting. And that's where I'm going to stop for now. And what this comes back to is we probably want to stop thinking about just the cost of those tokens and more looking at what is the value we're getting from the tokens and the cost spent, and how can we improve value compared to cost? Because obviously we want our cost to go down and our value to go up. And so there, I think we have to step a little back. And of course, as the token count goes down, our cost goes down, and but does our value go up? So we need to kind of align those two in a way. And I think one of the better ways, or one of the ways we can bring token count down, is by asking why our token count is high, by thinking about how we're interacting with our agents. Do you find yourself having to go back and say, no, not like that, like this? If you're doing any kind of code review yourself, do you find the same problems over and over again and having to say, fix this, fix this, fix this? Because of course, this just makes your token count go up and up and up constantly. Because the more code you generate, the more times you find the same thing over and over again, the more times the model then has to go back and fix the same problems. So this is where we need to find deterministic solutions that prevents the model actively from going down that road in the first place. So we need to keep an eye out for these repeated mistakes that happens. And so that is why, like some of the things that I'll be talking about in other videos is so critical in how we set up our fast feedback loops, our linting, our testing infrastructure, the guidance that we provide to these models. But we need to lean much more towards deterministic means of doing this rather than just suggestive via skills and things like that. Those are valuable, but the things that are really valuable is when it becomes deterministic. And I found some ways that I really think is making a measurable difference. And I think that is where we need to, if you continuously, if you run, for example, AI code review, and again, you see there, it keeps raising the specific problem time and time again. Don't just keep telling the model, no, fix it, don't do that again. ask yourself, how can I best prevent this from reoccurring in the next pull request, in the next set of work that I'm doing? And find the tools and methods and means to put those deterministic guardrails in place so that we can drive those token costs down in a meaningful, repeatable way across models and across tokenizers so that we can increase the value while lowering our costs. I think that's a much more, that's a long term, it's a better approach than trying for like these small little wins that then can be blown away by tokenizer changes and stuff like that. Um, this was a long video and there was a lot here. I hope it's interesting. If it's not, well, I found it interesting. So there's that. But if there's anything, questions you have, or anything that I might have missed, or anything you want to dig in deeper, let me know in the comments and I'd be happy to have a conversation, maybe make another one of these, digging into one of those specific topics. I find these things really fascinating, and maybe you do too. So until the next video, which might be something like this or something completely different, I have no idea. I will speak to you soon, and have fun. Have fun building cool things and learning, learning. It's the time for learning is not stopped. It's now more than ever. There's so many more things to learn about. So have fun out there, and build great products and great solutions that actually moves humanity forward. And I'll speak to you soon. Bye.